All right, so we're going to go ahead and get started. Thank you, everyone, for joining us today for Journey into Engineering at UAA. My name is Nicole Massey, and I'm the first year advisor for the College of Engineering. And this means that I'm the one that helps all new students to land at UAA with your feet planted right in the right direction, because we want our students to be focused on what really matters, which is your studies and your goals. So we do everything we can to put you on the simplest path towards graduation. Before we get into the presentation, there's just a few things I want to go over before we get started. So first, just a little bit of Zoom etiquette. Some of the guidelines we're asking everyone to follow tonight is please keep yourself muted unless you're speaking to the group. Just in case you're not familiar with Zoom, the mute button is on the bottom left of the screen and it looks like a microphone. When you're muted, you'll have a red slash going through that. If your video is visible, just please be aware of what's going on around you. Most of us are in the home situation. So if you have a lot going around, you feel free to turn your camera off if you need to. We will have time for questions at the end of the event, but please also, you can ask questions in chat and we'll do our best to answer them as we go along. So please just be respectful of everyone involved in Zoom today. The first event today is broken into 3 parts. First, we have a demonstration by Dr. Hamel from the Department of Civil Engineering, and he's going to introduce himself in just a moment. And then second, we'll have a brief presentation about the UAA College of Engineering and what our programs can offer you. And then lastly, we're going to open it up for questions, and we're happy to answer any questions about the demonstration or about the college. Okay, does everybody, anybody need me to repeat anything? All right, I'm going to turn it over to Dr. Hamel.
All right, can you hear me?
Yes.
Hi, everyone. As Nicole said, my name is Dr. Hamel. I am a professor here in the Department of Civil Engineering. And before I tell you a little bit about civil engineering, I thought I would give you a little demonstration of what we do here, or one of the things that we do here. And this is a little bit like one of the classes that you take here in civil engineering, where we basically break things. It's called Smash Lab. And the idea is that we want to know how strong things are, both because sometimes we don't want like buildings and bridges. Sometimes we do want things to break. Like if you're doing, if you're designing an icebreaker, right? A boat that's going to break ice, you want to know how strong the ice is so that you don't break your boat, right? You want to break the ice, not the boat. And so we test all kinds of things in your class. It's a sophomore level class, and we test concrete, we test steel. And so the demonstration that I'm going to do for you today, I'm actually going to break ice. I have made a beam. You cannot see it yet. It's going to be down here. But I have made a beam out of ice. It's in the freezer. I'm going to run and get it. And then I'm going to, this vertical green thing here is what's called an electromechanical actuator. And it can push down with, let's see, this one is a 2,000-pound actuator. So we can push down with 2,000 pounds. And up here on the screen, it'll tell you how much load it's actually pushing down with. So, so that's going to happen a little fast. That's why I want to tell you about it beforehand, because it's ice and it melts. We do actually have the ability here in the College of Engineering to do the whole thing in the cold so that the ice doesn't melt, but it's a lot harder to get the cameras into that space. And so we're going to do it here. So, all right, I'm going to run and get, afterwards I'll talk about why I have a giant wrench. So I'm going to run and get the ice. I'll be right back. All right, so it turns out ice is heavy when it gets this big. If you'd like to figure out how heavy it is, it's 6 inches by 6 inches by 48 inches. And ice weighs about 55 pounds per cubic foot.
Dr.
Okay,
Hamel, sorry, we had a question. Which specific class would our students conduct a lab like this?
it's called Properties of Materials, 334.
Thank you.
All right, so in the black area, you'll see a graph that shows how much displacement or movement the actuator on the x-axis, and then the up and down. Gosh, I hope we can break this. This is a big piece of ice. The up and down is the load. I don't know if you can see the graph, but you can just watch the load here. The graph will keep kind of going up, and it's kind of, the numbers are super small, and it's kind of auto scaling, so it's not super useful, but okay. Oh, I'm upside down, so this is okay. Here we go. We already got 40 pounds on it. Oh, does anyone want to guess how much it'll hold?
Maybe 200.
200.
Maybe 130.
Well, there's 200.
Oh, never mind. Too late.
Oh, you can see the cracking. The cool thing about ice is you can see it break. It actually breaks exactly the same way that concrete breaks, except you can see the cracks. There's 400. 500. 600.
Now I'm starting to guess 1,000.
Uh-oh. Ah. Nice. Cool. So this is exactly the same way that a reinforced concrete beam would break. And you can kind of see we spiked out at about 720 pounds. And one of the things that we did, which you can kind of see, is we put pieces of wood inside of it, and that's why it's didn't completely collapse. And the wood, it's kind of funny about this. I'm just going to bring it back up so you can kind of see it. The wood kept it from breaking, even though, if you tried to make there we go, you can kind of see the wood there. And that's exactly what we do with concrete. We put steel inside of concrete, and that keeps it from cracking and breaking. So it's kind of a fun test to see this. 700 pounds, it's quite a bit of force there, right? Yeah, any questions about, I was going to talk about something else, but I can't remember. Oh, I know what I was going to say. These, it turns out that these dowels are way bigger than I wanted them to be. But I had one of the cool things about UAA, as opposed to bigger research universities, especially outside the state, is that there's a lot of opportunities to work in research and for professors in their laboratories when you're an undergraduate, because we don't have huge graduate programs, and so a lot of students will work as an undergraduate. And one of my undergraduate workers actually made this ice beam, and he put pieces of wood in that were way bigger than I asked him to. So that's kind of funny. So the wood is not going to break because it's huge. You can kind of see how thick that wood is. Really, all you need is like little tiny 1/4-inch dowels. All right, I'm gonna put this in here so it doesn't melt all over my floor. So one other thing I wanted to mention is it's a little bit hard to see because it turns out that the two things are kind of aligned, but the green thing you see here is just a little baby frame that I have for breaking things like this. I've done a little bit of research with them. The big red one that you see kind of overhead, that's the primary structural engineering lab. And so this is used mostly for research. We do use it a little bit in timber engineering. It has a 100,000-pound actuator that's kind of hanging in the middle there. And so sometimes we hit things. It's actually set up for a test right now on a footing that sits on the ground. And we probably have to put about 50,000 pounds on that. to get it to break. So that's kind of exciting. It's kind of fun to work in here with the big steel. That's why I have a giant wrench, because the steel is really big, and so that's kind of cool. All right, before I move on to talking about civil engineering and UAA, are there any questions about the demonstration or the lab?
Why didn't the wood break? Kind of
Yeah, why didn't the wood break? Because it's too big, right?
So you mentioned like the ice is kind of like a concrete block. Is there any reason like some ice is stronger than the others?
Well, that's a good question. So ice is one of those really cool, fascinating materials where it has a huge range of strength, and it has to do with the amount of air inside the ice. It has to do with the way that the crystal orientation. So like surface ice that forms on the surface, the crystals grow left to right. And so there's a lot of variables. If it's salt water versus fresh water, if there's silt in it, it will weaken it. And so ice is a really cool material. We're actually getting into doing a little bit of research on ice. But yeah, you can spend your whole career on ice if you like ice. Good question.
Is this press hydraulic or is it a different type of press?
So the little guy is electromechanical. The one behind it, which is like a little bit hard to see because it's right in line with it, that one is hydraulic. The 100,000 pound one is hydraulic. We have a 100,000 pound and we have a 200,000 pound. They're both hydraulic. So, any other lab questions?
How many pounds would it take to like break a beam made out of concrete?
Good question. Similar sized, I have no idea. I would actually have to do the math. So one of the things that sometimes I teach reinforced concrete design, and I teach you how to actually do the math. If you have a piece of concrete that's it would be a whole lot heavier than the ice for starters. Actually, it'd be about twice as heavy. And if you had the same size beam and you had little tiny pieces of steel in it, how much you can do the math and figure out roughly how much it would take. I would guess it would probably take about I don't know, 5,000 pounds maybe to break that size beam, something in that neighborhood. That's kind of a guess, but I could do the math for you.
Assuming that if it does break, would it like shatter completely or like would it explode?
So one of the reasons I mentioned that the ice is similar to the concrete is that it would actually fail exactly the same way as the ice did. The concrete would sort of start cracking in the middle, the cracks would work their way out, the bottom pieces we call it spalling, would kind of explode off in a brittle, explosive fashion. But the piece, if there's most of the concrete and bridges, there's steel inside, buried inside the concrete, it would bend, the steel would bend and it wouldn't break and it wouldn't let the whole beam break all at once. So basically exactly what you saw, except more force. And actually instead of ice dust, you would end up with concrete dust. Little bits of concrete dust would go everywhere instead of, we have a puddle of water here. But it's much easier to clean up an ice beam than a concrete beam. Concrete's super messy. So, is that good on time? I don't know how long I can answer questions about structures lab all day, but okay. Any other questions? Oh, I forgot other things that we break. One of the big projects that we have is, I was looking for a small piece of one. We have these SIP panels, which are foam and concrete, or sorry, foam and plywood. I'll just grab this one. A little bit big, but. So some of you may have houses built out of this. It looks like this. It's got 5 inches of the foam and then the plywood on the side. And so we break this to see if you put it in your house. The cool thing about this is that it's super light. So you can build a house in about 3 days with this. And it's super insulating. has about twice the insulation of a typical house. And so, so we've done all kinds of stuff with that. We've broken timber beams, we've broken concrete beams. We broke a steel beam, although we didn't actually break the beams, we broke the bolts that were bolting the beam. And right now it's actually set up for a square footing. So we're gonna basically poke a hole in one of these that would basically sit on the ground flat, and you put your house on top of it. So lots of stuff. It's fun to break. We've also done seismic tests where we go back and forth, just like a seismic, like an earthquake, which is kind of fun. So lots of fun stuff. All right, so structural engineering, or when you learn about materials, I don't have to keep the gloves on, is one part of civil engineering. Civil engineering is when we learn all about the different things that, so we talk about transportation, marine highway, air traffic control, that's all transportation engineering, runways. We talk about geotechnical, so soils. You can learn about rock and drilling into rock and building things with rock, or building things with concrete against rock, retaining walls, things like that. We also cover in civil is very broad. We also cover environmental. So if you spill oil into the soil, how do you clean that up? Is it wet? Can we, do some testing to figure out when it's cleaned up? And then we also cover water. So pipes and clean water, filtering clean water, keeping the pipes with pressure in them. So there's all kinds of, basically anything that you rely on or want to build for your community to make your, life sized. Clean water, wastewater. I have a friend who specializes in poop, right? That's pretty much what he does. So that's kind of funny. So water, wastewater, roads, bridges, structures. Structures are a lot of fun in Alaska because we're in an earthquake zone. So there's lots of science and learning about how to design buildings that are tall but won't fall down in an earthquake. So those are kind of all the things that we study here at UAA in civil engineering. And there are other forms of engineering: mechanical engineering, electrical engineering, geomatics, which is like surveying. We also have computer engineering and computer science. I missed one. No? Oh, project management. I think that's all of them. So a whole bunch of different varieties of engineering. Civil engineering is actually the most opportunities in Alaska. A lot of other places you'll find more mechanical engineering, people that design and build cars or cell phones or planes. But here in Alaska, we don't have a lot of needs roads and bridges and water and wastewater. And so civil engineering is by far the largest. There's the most civil engineers in the state of Alaska. So why is it great to come to UAA? Well, for one, it's right in the middle of everything. One of the great things about our program, one of the classes that I teach is called Senior Design. And then when you get through your 4 years, you get to be a senior, and you do this one class. It's called Senior Design, and you basically are given a project to design from start to finish. Most of your other classes, you learn about the little steps within the design, but when you're a senior, we just give you a project and we say, design it. And the cool thing about being in Anchorage is that you get to do that with actual projects and actual mentors from real engineering companies. And Anchorage is the hub of engineering in Alaska. All the companies, all the engineering companies are in Anchorage. A couple of them have other offices, secondary offices in Fairbanks and Juneau. But there's nobody that doesn't have an office in Anchorage that I'm aware of. And so we use those people to come and talk to the class and to mentor students in those senior design classes, and also to do internships. I actually, believe it or not, as cool as this lab is, I have a hard time getting students to come and work in this lab. And I know you find that surprising because who wouldn't want to use a wrench this big, right? It's a lot of fun to use a wrench this big. But I have a really hard time, and the reason for that is there's so many internships available and so few civil engineering students. The engineering companies hire all the interns, and then I can't hire them because they can pay more than me, frankly. And so there's always a little bit of a struggle there. The advantage to working for me is that you can drop in, you can go to class, then you can, classes are right upstairs. You can drop in here, work for an hour, go back to class. So that's useful. So yeah, so that's kind of one of the, I would say those are the major advantages to UAA, beyond the fact that it's a beautiful campus and, it's a lively campus. It's the biggest campus in Alaska, biggest university in Alaska. Nicole, did I miss anything big? Do you want me to talk about?
No, I didn't. Think you hit all the really important touch points there. Do you guys have any questions for us?
Yes, I do, but it's kind of related back to when you're talking about the house foundations and how you guys would test it. If you were to just test one point in like a little testing foundation, wouldn't it be kind of like, it wouldn't be a right like estimate or anything because you're just doing one point? How would you like balance out all the weight, because a foundation's supposed to take all the weight at once?
Yeah, well, that's a good question. So there's two ways that we can deal with that. The first one is that when I design a foundation, I don't design it for point. We call those point loads, right? Like a single, like this, like the actuator, a single point, or the giant actuator behind it, single point. We don't generally design foundations for point loads. We design them for what's called line loads. So we basically design the whole wall for a constant load. And the idea is that at any given point, that load will roughly be the same. Obviously, it's not actually the same, right? As you go along the length of a house, there's going to be a variation depending on, if you have a jacuzzi up on the second floor, there's going to be a little bit more weight. But what we do is we spread the load out so that it works. The other side to that is at any given point, there's going to be strong soil and weak soil. That's kind of the nature of soil, right? You're going to have an air pocket somewhere. You're going to have a rock somewhere. And so again, we use statistics to kind of basically figure out what is a good average or a conservative number to use for the strength of soil. And so statistics is a class that you take. I think it's a junior level class. Engineering, it's basically engineering statistics. And it teaches you all about the statistics that you can use to basically approximate what the strength of soil is. So yeah, that's a good question. Any other questions?
Do you use other materials besides concrete for beams?
Yes. In fact, I don't actually like concrete very much. I'm the steel and wood guy. I teach steel and wood. There's another professor, the other structural guy, he teaches concrete. And it turns out that concrete, especially, your guys' generation, concrete is not a very green material. In fact, it is the opposite of a green material. Concrete is the worst offender of greenhouse gases that there is. Now, it's a very evil sometimes because you just can't build bridge foundations out of anything else. There are certain things that you have to use concrete for because we haven't found anything else that works as well. But if you're building something or a small, a Walmart or, a one-story strip mall or something, sometimes they use concrete because it's cheap, especially not in Alaska. We use concrete for, like in Phoenix, they use a lot of concrete, and it's just, terrible from a carbon polluting standpoint because something like 13% of the total greenhouse gases in the world come from just making concrete. And so I attempt as much as possible to make beams out of things other than concrete. We make them out of steel, we make them out of wood, I make them out of foam. One of my structural polymers. So can we make our beams out of plastic? So yeah, I am a big fan of not concrete. Anything, and actually there's a really cool movement right now to build huge slabs of wood. So that's kind of something that's growing. They're talking about building 10 and 20-story buildings out of wood, which they haven't done since, you know, sort of the turn of the 20th century when they got worried about fire. So that's an up and coming thing. So hopefully we'll see more of that. Good question. Any other questions? Maybe about anything about the program? What does a civil engineer do?
How close is the you're in the main engineering building. How close is it to the dorms? Like either driving distance, walking, whichever
Good
one
question.
is.
I would say it's about a 8-minute walk. I
Give
would
or
say
take.
8 to 10-minute walk. One of the cool things about the engineering building is it's right in the middle of campus. We have a cool bridge that goes over, and this cool arch bridge that goes over the main thoroughfare, Providence Drive, which is a little bit dangerous to walk unless there's a stoplight. So that we go over the bridge, and then it's actually a really cool walk through. Most of the property is actually the hospital across the street. The dorms are on the far side of the hospital, but it's mostly through the woods, and there's it's a really pretty walk. So yeah, it's definitely walkable. I would not drive it. Parking here is actually gotten a lot better since they built the engineering parking garage. Parking used to be a nightmare. It's not too bad now, but if you live in the dorms, you want to walk or ride your bike. But you could probably go from one end of campus in walking is probably, it's kind of a long, skinny campus, so it's probably 20 minutes from one end to the other. A lot of people ride their bikes. The other thing that's cool about it, which I don't understand why UAA has this and UAF does not have this, but there's a spine that's indoors. It runs almost the entire length of the campus, which means you don't have to go outside. It's not quite connected to engineering yet. You got to shoot across just a really short little outside space, but for the most part, you can make it from one end of the campus without going outside, which is pretty cool. In the winter, you get to go over this really cool stream waterway that's like half frozen in the winter, but you're warm. So it's pretty neat. I don't know why UAF doesn't have a series of tunnels. It gets a whole lot colder up there, but for some reason we got the tunnels. Or they're not tunnels, they're elevated walkways.
We also have the Seawolf Shuttle too. So
Oh, yeah.
if for some reason it's heated, you can catch it right outside of the residence halls, and it'll take you to every major building. And it runs on approximately a 15-minute loop.
That's good. I forget about the shuttle. Any other questions?
I may have forgotten this or not heard it, but what would you use that wrench for?
Good question. So this whole frame is put together with huge bolts because one of the things that we do is we reconfigure the frame depending on what we're trying to break. That actuator can go vertical, it can go horizontal, and so we have these huge nuts and huge bolts to hold the whole thing together so that it can all get taken apart. We actually have a 10-ton crane in the room, so it picks up all this stuff and puts it all down. We can actually clear this entire room out so there's nothing in it. And the frame actually sits on this special concrete floor, which is 3 feet thick. And the columns bolt down into the floor. In fact, I'm rusting one of the bolt downs as we speak because there's a little puddle on one of them, which I really shouldn't do. But there's these hold downs that go into the floor, and the big wrenches are used for tightening the huge, all the huge bolts. So we have this one, and we also have just a regular wrench. This one's a little bit, easier to hammer on and stuff. So yeah, that's what we use the big tools for big hardware.
Are there any other questions?
What's that? I do. Yeah, if they want to see it break. I have another ice beam if you guys want me to break that one too.
I think the consensus is yes.
What's that?
The consensus is yes.
Okay. All right. Here's my gloves.
See if we can get everybody to type in a guess at how many pounds this is going to take to break. 1550, okay. 900, all right.
Did anyone figure out the weight? No, the weight. Yeah.
800.
Whoa. All right, so I'm going to reset this. So 718 was our last beam. Oh, I forgot my compliance block.
Did you program the beams like coding to go down and up yourselves?
Oh no, I'm pushing a button. That would require way more programming than I'm capable of. I did build the data acquisition system though. Like all this is programming that I did. And there's a whole box here that's got transistors and circuit boards and power supplies, and we had to build all that. So we definitely leaned on our brothers in electrical engineering for that. All right, I'm going to reset this again. And here we go. Oh, that was quick. So you can kind of see, I don't know if you can see this, but it'll go up and then it'll drop down and then it'll go up again. That's the cracking. It actually loses strength a little bit when it loses force when it cracks. Like I said, concrete does the same exact thing. And you should see the cracks propagate from the middle toward the edges, because most of the force is in the middle. Whoa. Whoa. Oh. Break. There you go. That's kind of fun. So the other thing that you're supposed to do, so we got to 680, so this one was weaker. You're supposed to, the other thing that my student was supposed to do is you want the reinforcing, the wood, or if it's in concrete, the steel, you want it to be at the bottom of the beam, because this is what's going to happen is basically the bottom part becomes useless. But he kind of put it in the middle of the beam, and so we would have gotten more strength, I think, if it was near the bottom of the beam.
So if the beams were thinner, would it, like the dowels, if they were thinner, would it be stronger or weaker?
So that the dowels were thinner, it would probably not actually change the strength that much. Because right now they're oversized, and so they're not actually helping. So there's a critical point at which the dowels will no longer, when you make them bigger, you just keep making them bigger, they're not actually helping anymore. there's a point where if you made them tiny enough, then you know, it would start getting weaker. But once you hit a critical size, basically it has to do with the strength of the ice. Once you hit that critical size, making them bigger doesn't do anything. So you could make them smaller, you'd probably get the same number. Now, if you moved them lower in the beam, you get bigger numbers because of the way the mechanics of the stresses inside the ice works.
How would you make these? Do you have like some sort of freezer mold that you put these in, and then you just wait for a couple of days or something?
I couldn't hear that.
You have like a mold. How do you make the?
Oh yes, that was an engineering project in and of itself. We have a mold, but the tricky part of the mold is that you had to figure out how to be able to get the beam out. And so it's basically thin metal in the shape of the beam, but it's got two steel plates on the ends, and then there's some threaded rods that squeeze it, and then we pour it, and then we're able to pull the ends off. And we built that in the machine shop here after some trial and error. We actually also have a smaller one. Actually, I think it's really right here. No, it's not. I thought it was sitting over there. I don't know where the smaller ones are. We have smaller ones too, but the big ones are more fun, right? So, what? Oh no. So the reason that we're able to build these is because one of the other labs that we have is called the Cold Regions Engineering Lab, and it's basically two huge 10-foot by 10-foot walk-in freezers. But it's not like you're, you know, a meat locker in a restaurant. I mean, it looks similar to a meat locker in a restaurant, but we can actually control the temperature to within ½ degree. And we can change the temperature, and it can go all the way down to minus 30 Celsius, which is about, I don't know, minus 25 or minus 35 Fahrenheit, I think. They're almost the same. They come together at minus 40. So that's pretty cold. And we have another thing in that same lab, which is this huge machine, and it's got a little space about 2 feet by 2 feet by 2 feet that we can bring down to minus 70. So it's super cold, which is about 94. I think it's minus 94 Fahrenheit. So pretty cool. Fun. We can freeze pretty much anything. We could actually bring this entire setup inside the cold room and do this inside the cold room. We've done that before where we bring equipment in. Right now we have a project going on with the Port of Anchorage where we bring ice back from the port and then we keep it in there, and we actually cut specimens inside the cold room. So we have a bandsaw and a chop saw and a lathe, and we put them inside the cold room and we make these cylindrical specimens that we can then break in compression. So that's a super useful piece of equipment that we have, and we get to do all kinds of research related to the Arctic and cold weather. So it's kind of fun.
I have a question, kind of on like what you just said about the cylinders. What would happen if you tried to break it like vertically? Would you put the wood in the same spot, or would you like?
So good question. Typically, for ice and also concrete, we break cylinders. I actually have a whole bunch of them in the freezer right now because of our port project. We break a cylinder and we just squish it and we don't put any wood in it. Because what we're really after is the strength of the ice or the strength of the concrete. We don't, in this case, we could do the same thing with the beam, right? We could build a beam that has no wood in it, but it wouldn't be very exciting because as soon as it has its first crack, the whole thing goes down. And that's why we don't build concrete buildings without steel inside, because as soon as there's a crack, as soon as you exceed the capacity of that, the strength of that beam, the whole thing falls down. Whereas in compression, it's actually ice and concrete are both really good in compression. And so we want to know, similar to the previous question about, what controls the strength of the ice, like, how much air is inside of it, how much salt water is inside of it, how much silt is inside of it, what are the size of the crystals, how did they grow, what temperature, you can make ice really fast, right? You can take some water and then put it in like -30 and make fast ice, or you can make ice really slow. You can put it at -5 Celsius, just barely freezing, and take a long time to freeze it. You'll get two different kinds of ice. And so we want to be able to characterize or understand that ice. And so a cylinder in compression is how we do that. And that way we have a standard, if you will, a similar test that's always the same. And then we can talk to other researchers and say, oh, we found this ice to be this, we found it to be that. And so that's how we do. Now, it holds a lot more in compression. The first one we did, I think it held, I think it was about 1,000 pounds. And it's a little cylinder about this big. It's about 2.5 inches in diameter, and it held 1,000 pounds. So ice is pretty good in compression, same with concrete. Steel is even better in compression, but steel's very heavy, right? Steel's 3 times as heavy as concrete, and 10 times as heavy as wood, or 10 times as dense as wood, really. Lots of good questions. I could go all day. Can I use my joke? Can I use my inappropriate joke? Just one? What's the difference between a civil engineer and a mechanical engineer in Alaska? Anyone? The civil engineer has a job. Oh, ouch. My mechanical engineering program doesn't like it when I use that joke, but. Yeah, they need to get one, yeah.
I do have one more question.
Shoot.
Over the years, have you ever found anything, like at least one thing that has withstanded the strength of your presses?
Yeah, actually. Where did it go? I think it's outside. So when we got our new 200,000 pound press, we built this piece of steel. We wanted to crush a piece of steel like a soda can. And so we got this piece of steel, and it was about it's a hollow square. It was about this tall. It's about 6 inches by 6 inches or 8 inches by 8 inches with about 1/4 inch thick wall. So it was like a pipe, but square. And we put it under there, and we tried to squash it, and we couldn't do it. So that was kind of sad. So when we drilled a bunch of holes in it, and then we squashed it, and then it worked. But I still have it. I think it's outside. We run into a little bit of a problem of storage space in this lab, so we end up putting things outside. But yeah, so that was kind of exciting. Actually, it was disappointing when we first did it, because we wanted to squash this piece of steel like a tin can. But you know, so there's other labs that are much bigger than ours. This is the only working strong floor in Alaska. If you go down to the lower 48, some people have 1,000,000 press. So you can really break some stuff with a 1,000,000 press. But this is the only one in Alaska. So Fairbanks has a floor like our strong floor, but there's nothing on it. They don't have a frame or a hydraulic system or hydraulic actuators. It's just a floor right now. So yeah, so it's kind of fun. It's a fun question. All right, well, nice. Any other questions about living at UAA, being at UAA, living in Anchorage? Is it scary to live in Anchorage? No. I'm from Boston, so Anchorage seems small. The chat? Nicole can't see them all?
Mm.
Oh, does anyone have a question? No, okay.
All right, so if there's no further questions, that was a no.
I need to clean up my puddle, so.
Okay, so that brings us to the end of the show. We really appreciate everyone in attendance. I hope that everyone had fun learning about the College of Engineering and Civil Engineering today. And I want to encourage all of you to reach out to us if you have any questions, especially with application or admissions. I very much look forward to the opportunity to meet you all in person once we're out of the virtual world here. We call this event Journey into Engineering because we really believe it's our duty to help guide you on the path towards achieving your goals. Becoming an engineer is a journey and nobody should go that journey alone. If you have any questions, please feel free to reach out to me anytime. We're always here to help and to help get you where you want to be.